In this video, I'm going to cover mathematical induction and what it really means and how it works. I think a lot of people know how to use mathematical induction to prove propositions and a lot of formulas, but they don't really understand why mathematical induction works the way it works. So that's going to be the main focus of this video, to really understand mathematical induction. And then I'm also going to apply this form of reasoning to a proposition so that you guys can see this form of reasoning in action. So to understand mathematical induction, we first have to understand inductive reasoning. Now, inductive reasoning is just when you observe a bunch of data. You spot a pattern in this data, and then you conclude that this pattern must hold for a larger set of objects. Now, this is pretty abstract, so I'm going to give an example. Now, let's say that you've only seen 3 cats your entire life. You've only seen 3 cats. So these are your observations. Bruno is an orange cat. Bruno is an orange cat. Milo is an orange cat. And you've observed another cat. We've seen another cat, I don't know, called Buttercup. Buttercup is an orange cat. So these are the 3 cats that you've seen your entire life. And you might then conjecture, you might then propose that therefore all cats must be orange. So what you did here is you used inductive reasoning, right? You had a bunch of data, right? You observed a pattern in this data, cats being orange, and then you conjectured that this pattern must hold for all cats. This pattern must hold for a larger set of objects, the set of objects being all cats in this world. So this is inductive reasoning in action. So now we also have to understand deductive reasoning, because mathematical induction, even though it's called mathematical induction, it uses deductive reasoning as well. So deductive reasoning is just when you have a bunch of statements. You assume that these statements are true. And then you show that if these statements are true, then some specific conclusion must follow. So you show that if certain statements are true, then a specific conclusion must follow from these statements. In other words, the truth of the set of statements necessitates the truth of the conclusion. It makes it necessary for the conclusion to be true. So if the statements are true, then this conclusion has to be true as well. So this is deductive reasoning. Now, this set of statements are called premises, and the conclusion, well, it's just called the conclusion. So you show that assuming certain premises are true, a certain conclusion can be deduced. So if the premises are true, then the conclusion must be true as well. This is deductive reasoning. And when you combine these two forms of reasoning, deductive reasoning and inductive reasoning, combining these two forms of reasoning is what mathematical induction really is about. So mathematical induction is just inductive and deductive reasoning combined. Now, I'm going to give a specific example, but for now I'm going to speak pretty broadly. So first, like in math, you have a bunch of data, you observe a pattern in that data, and then you conjecture or you propose something. You state that this property or this pattern that I've observed is true for a much larger set of objects. This is your conjecture. This is called your conjecture or proposition that you've stated that you've stated using inductive reasoning, and then you use deductive reasoning to prove this conjecture. So you use deductive reasoning to prove the conjecture, and you produce that conjecture from inductive reasoning. Now, this is what mathematical induction is. Now, this is pretty abstract. So again, I'm going to give an example. So let's say you have a bunch of data. So here's your data set. Now we can also write these numbers. We can write these numbers like this. So I can write 1 as 1 times 1 plus 1 over 2. I can write 3 as 2 times 2 plus 1 over 2. And I can do the same with these numbers. 4 plus 1 over 2 and 5 times 5 plus 1 over 2. And on this data set goes. So we have some data here. And now you might have observed a pattern in this data set. And after observing this pattern, you might conjecture that the sum of the first n numbers, can be expressed as n times n plus 1 over 2. Right? This is the pattern we observed. Each term here, or only these two terms, are being increased by plus 1. So you might conjecture that the sum of the first n natural numbers can be written as n times n plus 1 over 2. And this holds for the natural numbers. Now the natural numbers are just, the set of numbers like 1, 2, 3, and then all the way to infinity. So you had some data here. You were given some data. And you observed a pattern in this data. And then you said that this pattern holds for the natural numbers, all the natural numbers. So you use inductive reasoning to produce this conjecture. Right? Now, we can prove this conjecture using deductive reasoning. So here's a conjecture that we produced using inductive reasoning. And now we're going to prove this using deductive reasoning. So how do we do that? Now remember that deductive reasoning is just when you have a bunch of statements, or even just a single statement, you assume that these statements are true. And then you show that if these statements are true, then a certain conclusion must follow. In other words, if these statements are true, then a certain conclusion must follow. So this is deductive reasoning, and this is exactly what we're going to do here. So we're going to assume that a statement is true. Now what statement is that? Pk is true for all k in the set of natural numbers, and where k is greater than or equal to n. In other words, we can also write a statement like this. So Pn is true for all n is equal to k, where k is in the set of natural numbers. So these statements are just the same thing. So this is the statement. I'm going to stick with this one for now. So we're going to assume that this statement is true. Right? We're going to assume that this statement is true. I'm going to write this right here, assuming to be true. And these two are the same statements. Okay, these two are equivalent. Okay. So we assume that this statement is true. Now we must deduce a conclusion. Now the conclusion we're trying to deduce here is that pk plus 1 is true. And the reason why we want to deduce this conclusion will be clear in a minute. So we've assumed that pk is true for all k in the set of natural numbers. And now we're trying to deduce from this truth that pk plus 1 has to be true as well. So this is how we do that. Now, because we assumed pk is true, we can write our conjecture like this. 1 plus 2 plus 3 ... plus k, and k into k plus 1 over 2. Right? This is what we've assumed to be true, this statement. And now, let me just add a bit of space here. And now we must deduce that if pk is true, then pk plus 1, that pk plus 1 is true as well. So this is the statement that we have to prove is true as well, pk plus 1. And let's just simplify this a bit. So I can write this as k plus 1 times k plus 2. K plus 2. Okay. So let's try to reduce pk plus 1 from pk. Now we can rewrite pk plus 1 using pk. And how do we? By just writing this sum as 1 plus 2 plus 3 dot 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 plus k plus 1. Right. Now the reason why we can introduce a k here is because the term, like the term that is just one unit below k plus 1 is just k, because this is the sum of the first n natural numbers. So 1 plus 2 plus 3 plus dot 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 plus k plus 1 is the same as this, right? We've just explicitly stated the k term that comes before k plus 1. Recall that this is the sum of the first k natural numbers. So we can rewrite this pk plus 1 statement like this. And this, of course, has been conjectured to be equal to k plus 1 times k plus 2 over 2. And because we've assumed that pk is true, we can substitute this entire statement right here. Because 1 plus 2 plus 3 plus k is like the same as this part of the statement. So instead of 1 plus 2 plus 3 plus k, I can just write k times k plus 1 over 2. So instead of this part, this entire chunk of math, I can write k times k plus 1 over 2 plus k plus 1. And now I can simplify this and let's see what we get. So let's see whether this is equal to k plus 1 times k plus 2 over 2. Now simplifying this is fairly straightforward. All you have to do is cross multiply. So I'm just going to do that pretty quickly. K plus 1 over 2. Simplify this further by writing this as k times k plus 1. And actually, let's just take k plus 1 common. So if I take k plus 1 as a common factor, then I can write this as k plus 1 times k plus 2 over 2. Now this is equal to our right hand side. So this means that if pk is true, then pk plus 1 has to be true as well. If pk is true, then pk plus 1 has to be true as well. In other words, the truth of pk necessitates the truth of pk plus 1. If we know that pk is true, then pk plus 1 has to be true. Now the reason why I'm stressing this so much is because this is pretty much the essence of mathematical induction. Okay, so now we've shown that the truth of pk plus 1 follows from the truth of pk. But how does this exactly prove our conjecture over here? Well, to prove our conjecture, we have to perform one more step, and that's this. Our conjecture here proposes that the sum of the first n natural numbers is n times n plus 1 over 2. The first natural number is 1, right? And then it continues to 1, 2, 3, 4, and then all the way to infinity. So I'm going to see whether this conjecture holds for n equal to 1. Now n equal to 1 would yield 1 times 1 plus 1 over 2, which is just 1 times 2 over 2, and this is just equal to 1. Now the sum of the first natural number with nothing is just 1, right? So we know that p1, this was p1, we know that p1 is true. So the conjecture over here holds for p1. Okay, and we've already proved that pk plus 1 follows from the truth of pk, where k is a natural number. Right, now because we've proved that p1 is true, we can substitute 1 over here, and then we'd get, if p1 is true, then p2 must be true. And if p2 is true, then p3 must be true. You again substitute 2 here. And if p3 is true, then p4 must be true, and on this goes. And hence this proves our conjecture over here. What's the conjecture? Yeah, here's a conjecture. So this proves our conjecture. Now again, I'm going to repeat this. So First, we try to show that if pk is true, then that necessitates the truth of pk plus 1. And then we showed that our conjecture holds for the first term of our sequence. So it holds for n equal to 1. And because it holds for n equal to 1, and we know that pk plus 1 is true whenever pk is true, we can conclude that Pn is true, our conjecture is true, for all n in the set of natural numbers. And this entire deduction is called mathematical induction. So even though mathematical induction uses both inductive and deductive reasoning, we still refer to it as mathematical induction. So to summarize, mathematical induction is just a combination of inductive and deductive reasoning. We use induction to conjecture a proposition, like to produce a proposition, and then we prove said proposition using deductive methods. And this entire process of proving is called mathematical induction. This entire process of proposing a proposition and proving it is called mathematical induction.